Good day and welcome to yet another PROKON webinar. Today we will be discussing what's new in PROKON 5.1. Let's have a look at the agenda for today. There are four major topics that we will discuss. First, the new Sumo features. We will then look at the two exciting new modules, and then we will discuss the crack width calculations in continuous beam and the updated Eurocode Annexes. Your host for today is myself, Heino Snyman. Johan du Plessis will be our presenter, and in the background we have Chantay Tucker to answer any questions you might have. Please note that all attendee mics will be muted for the duration of the webinar. You can post questions in the Q&A section, which will be answered during the webinar. There will also be a quick Q&A session at the end, where your questions may be answered live. And now, without further ado, I will hand over to Johan. Johan, please take it away.
Thank you for the kind introduction, Heino, and thank you to all our attendees for joining. We are excited to have you here and to learn about the new additions in PROKON 5.1. So as Heino said, we will start by looking at the new features that have been added to Sumo, and there are 10 major ones that we would like to highlight for you today. And some of them are much bigger than others, but they are all useful nonetheless. So let's get into that. So at first, we've got the solid finite elements. So that's quite a major addition to Sumo. It's really going to expand the types of problems that you can tackle in Sumo. Then we've improved the efficiency for processing of large models. So that means meshing and the assembly of matrices. That happens a lot quicker in the background than in previous versions. Then in terms of productivity, we have improved the group functionality in Sumo quite significantly, and you'll see shortly in my demo what that entails. Then also we've enhanced the second order and nonlinear analyses, reducing the amount of iterations required to converge. So that's definitely something to look forward to. Then my personal favorite is the Python scripting interface that's been added, or PySumo as we like to call it. Then we've added a design link to the newly added module, the PileCap design module. So that's also available for you in the new version. Then we've increased the resolution for reporting purposes. So when you are exporting your screenshots to reports, especially if you want to print this to a PDF where people will zoom on it, you want that to be high resolution, and you can now choose which resolution you want to export those. Then we've also added support for 4K and now 8K screens. So Sumo is now able to support that, so you won't see any strange behavior there. It'll run smoothly on those very large screens. Then we've also added prescribed displacements to our supports, which is quite a nice expansion on that functionality, and you'll see that it's going to allow you to investigate some interesting things on structures such as soil subsidence, and see what the impact on the rest of the building is when that happens. And then lastly, with the whole BIM movement on everybody's tongue, we've added the support for IFC4 file format, which has been there, but we've now included the design transfer view, which is also very nice, and that cuts away a lot of the remodeling and things like that you have to do. So definitely look out for that. Right, so now we can have a closer look at each of these items. So the first one on the list here is the solid finite elements. So that gives us an entirely new finite element. Previously, we had the beams and the shells, which are still there, of course, but we've now added the solid finite elements, and that really takes Sumo to the next level, and it almost becomes a more general purpose finite element analysis program now, because you've got a lot larger variety of problems that you can solve with Sumo with these elements. Now, just to give you some background on these finite elements that we used, they are what you call incompatible displacement field finite elements. Now, Most other finite elements that you find out there in commercial software, they are what's called compatible displacement field finite elements, and it's very technical topic. We can have an entire webinar just on that, perhaps in the future. But I think what you must just know here is that your compatible displacement field finite elements, they give you what's called a lower bound solution, whereas these incompatible displacement field models that we've added here are actually, in our opinion, better for structural and civil engineers, because it gives you not the lower bound solution that you find with the other elements, but it gives you, so it's going to give you a lot more reliable results in terms of stresses and strains in the model. So definitely keep a lookout for that. And if you are interested in reading more about this, go and look up this paper here. We'll put the link to it in the chat. It's a paper published by Wilson and Ibrahim Begovic already in the year 1990, and it's titled "The Use of Incompatible Displacement Modes for the Calculation of Element Stiffnesses and Stresses." So quite a nice journal article there, and it does a good job of explaining what this finite element entails, and where you can use it. And we really believe that this is a good one to use. So that's something that you can look forward to. Right, now for the demo portion of this webinar, while I was preparing for this webinar, it was quite difficult for me to decide what I must show you, because the solid finite elements really give us the ability to model really any problem that we can think of, any elastic problem that we want to model, and that's why the options are aplenty. So what I decided was to just include as a first example this model of a twisted concrete beam. Now you'll see this model that I have here, it may not be the most practical in terms of design, but it really does a good job of demonstrating the capabilities of the solid finite element. So let me show you what's happening here. So as you can see, I've got the material that I have here is just a normal concrete with a 26 GPa Young's modulus, a Poisson's ratio of 0.2, so fairly standard properties there. And I've modeled this twisted geometry using the shell elements. Now you'll see that the analysis takes a few moments longer than usual, because there's 8,195 finite elements that I've included here. So you can imagine how many more degrees of freedom must be solved. And you'll see here, firstly, we've got our displaced shape. So these are your nodal displacements of this twisted beam. And it's quite a strange displacement that you see there, and that's just because of the nature of the model. You get this displacement in two directions, in the Y and in the Z direction displacement that we see there, even a little bit in the X direction too. And those of you that have worked with these types of things, you'll know that we can't model something like this using simply beam or shell elements. That's impossible. Looking at the stresses that we've got here, we've got our three stresses, our normal stresses, SX, SY, and SZ, then our three shear stresses, and those all make up the stress tensor. Then we get the principal stresses, S1, 2, and 3. Tmax is the maximum shear stress, and then SVM is the much talked about von Mises stress, that the criterion that we calculate at the end by combining S1, 2, and 3. And this is the von Mises stress in the beam that we see. So it looks like we've got about 12 megapascals maximum von Mises stress in this concrete beam. So again, not the most practical design problem, but really a nice one to demonstrate what you can do with the solid finite element. So really many problems that you can tackle. Right, and as promised then, I've got another example here, which is a lot more practical, and most of you structural and civil engineers will know what this is, and you might have designed this before. This is a model of a concrete pad footing, or also called a spread footing, that I have here. And instead of using a normal analytical method for this, we are going to investigate what happens to this when we apply a load. So there's a load in the X and Y and Z direction. So it's quite a complex loading, and we want to see what the influence on this on this support is. So you can see that I've loaded the nodes there at the top, 10 kilonewton downwards, 5 in the X direction, and then 2.5 kilonewton in the Z. So it's not a symmetric problem, this, which makes it more complicated. So we've actually got biaxial bending applied to this footing. And then I've got elastic supports there that represent the soil underneath this base. And when we perform the analysis, again, we're presented with the nodal displacements. You can see that this is quite an interesting displaced model. You can see that biaxial bending in the stub column at the top, it's bending about 2 axes. We've got our reactions in the soil, which are the springs. And then here we go with the solid stresses again. Importantly, the von Mises stress. So we can see on that corner there where the stress is at a maximum, we've got the von Mises stress. And if we zoom in a little bit there, we can see at that node what that's about 4.5, or let's round it off to 4.6 megapascals of stress, von Mises stress. That we see at that corner of the base, and that's obviously the most stress point. So, not a very interesting one. Perhaps something to do if you've got more complicated stuff that your normal design modules can't handle. You could throw that in here and model it, and then analyze it again. So here's another one, perhaps more for our civil engineering users. They might be interested in this. So what I have here is just a segment from a retaining wall that I've modeled with the solid finite elements. And you can see on the right hand side I've got loads, and then on the left hand side there's nothing. There's no soil providing passive pressure to this wall. So this is what you'll call a mass concrete wall, and this retaining wall relies on its own weight to resist the overturning soil on the right hand side. Now, getting the boundary conditions right here is quite important, and you can see that what I've done here is on the left-hand side and on the right-hand side, I've just restrained it so that it doesn't expand in that direction, because it is I've cut it out of a larger wall. And then again, I've got the elastic soil support underneath with the spring constants to simulate the soil underneath that. And if we look at our results, again, our nodal displacements, we can see what this wall does. And that's as expected, it's rocking about from the one side to the other. So you can really see the soil trying to overturn this model. Again, it's very simplified. It's only a linear elastic model that we've run here, but you get the idea, and it's a very good start to investigate something like this. And von Mises stresses, we see those concentrations there at the boundary conditions of the model, but it looks fairly good because it's decreasing as you go up with the wall to a value of almost 0, and that makes sense. So very nice. Just an example to show you what type of problems you can tackle with the solid finite elements. Right, so that's it for our solid elements. Now let's just have a quick look here at the processing of large models. Now, what we've done here is we've done a bit of the work and basically jumped ahead and make sure that the way that we process geometric models, so that's a slab, the way we interpret and process that into an analytical model, so that's what we call the meshing process. We're doing that a lot quicker now in the latest version of Sumo, and that's really what this topic is about. So you can see here, I've got this 7-story reinforced concrete frame, and what I'm going to do here is I'm going to mesh it, and you'll see that the meshing runs quite fast, and you'll have to trust me on that. That was not sped up. I didn't cheat. It's the legit time it took. So it's really a couple of seconds that we meshed this model in, and you can see all of the lift shafts, the ramps, and the slabs were meshed quite quickly. That really shows you how much of an improvement it is on that type of model. Right, then up next, as I said, in terms of modeling, you'll be a lot more productive now with the groups that we've improved. Now, those of you that know Sumo quite well, you'll remember that the groups have been around for a number of years in Sumo, and it's always been useful, but we've really gone out of our way and expanded the functionality, and you can now even create groups on the fly by just right-clicking on the model space and then creating it, and it works like most BIM software does these days. And the nice thing is you can create groups of different elements. You can lock groups, unlock groups, and once you've you've grouped elements together, those elements then behave as one object. So it's a block of elements, and if you then copy, move anything, any manipulations that you do on it, it then behaves as one element from there. So that's really the where you would use groups. So here with this frame, I've grouped the columns, the beams, and the slab together. And if I want to make changes to the individual objects in the element or in the group, I can simply unlock the group, and then that exposes the individual elements for me, and then make the changes that I want, lock the groups again, and then you can see now this group of elements, or this first story, is now treated as a block, and I can copy it and manipulate it around. So that's what's very nice about this. It even allows for nested groups. So I could create another group here of this building, and then copy that again. So the groups really will definitely speed up your modeling. Okay, then the next one that we have here is a small improvement. Now you won't see anything on the UI changing here, but we have in the background made some changes to the way the iterative analyses run. That's your second order nonlinear analysis. And what's going to happen now is fewer iterations will give you the same accurate results as you got previously. So we've really improved that process, and especially on a large model, you will see that runs a lot quicker in terms of your nonlinear and second order. So you'll see in this example, I'm going to run a nonlinear analysis with 10 load steps of this steel building, and again, this was not sped up. It's running very fast and quite efficient. So there we go. We've got our displaced shapes and then our results. So very nice in terms of buildings that show larger deflection, and also where you want to investigate sway, which is quite important on a steel structure like this. All right, so that's the enhancements to the second order and nonlinear analysis. Right, and then we got the Python scripting interface, or PySumo as we call it, and that's quite a big improvement and a adjustment that we've made to Sumo. And this really, I believe, takes Sumo, similarly to the solid finite element, it takes Sumo to the next level, because with the Python scripting interface, you can now automate some tasks in Sumo and really reduce your modeling time quite significantly. So before we get into that, just for the people that aren't familiar with Python, you may ask, what is Python, how is it used, and what are the benefits of learning and using this PySumo interface? So just to give you a quick introduction to that, Python is an open source programming language, and it's really one of the most used programming languages in the world, which is a good thing, because that means you've got a lot of libraries and things to access, and also a lot of resources to learn from, even free ones online that you can learn. Python it's an interpreted language, so as opposed to a compiled language, which really makes it perfect for scripting purposes, and it's a lot quicker to prototype your code using an interpreted language like Python. So that's really one of the reasons we chose it, and then also because it's so popular in the scientific computing industries. I remember I learned it at varsity. A lot of people, scientists, engineers, use it and know it, so it's just a natural fit for a program like Sumo. Then the question, how is it used? Well, it comes with the installation. We ship a little lightweight installation of Python for you. So it's included if you just update or install the latest version of Sumo. It's now included there, and that includes your basic libraries, things like the math library and so forth, just to get you going. And then you can obviously then expand on that by downloading other libraries if you're doing more advanced things as you go along. Then the benefits are quite significant. You can, with the Python scripting, you can really, for me, the most important thing is that you can automate boring or repetitive tasks. So if you do every week, you have to design a portal frame structure, for example, then create the script that sets up the template, imports the material, imports the sections, and you can simply just edit a couple of parameters in your model, the height, the span, things like that. And when you run that script, it just creates the model for you. So you can really save a lot of time doing that, and create your own templates. And another thing that that we quite often forget about is the way it allows you to parameterize your model. So you can really work in terms of parameters for your model and change a few things around, create a new model, change a few things around, create it again. So that type of repetitive modeling goes a lot quicker, and you can really build a lot more efficient models using the Python scripting. Okay, so and then just lastly, I talked about the libraries. You'll definitely see as you go along, you may want to expand that installation by including things like NumPy, which I use a lot in PySumo. You can even add pandas if you want to read data from a spreadsheet. That allows you to, if you've got large spreadsheets with data, you can use a library and use that data in Sumo to create your model. And then even SciPy and things like plot libraries, Matplotlib, Plotly, those things you can also use to create graphs of your own. So the possibilities are really endless in this regard. Okay, so to get into the first demo, again, I'm just starting out with a basic model. So what I'm doing here is I'm creating for you using this script. I'm going to create a cantilever beam, and just with a few lines of code, you can see there I've got a couple of parameters. What's the span of the beam? What's the depth? What's the width? I can change those parameters around, and with a couple of for loops there, you see where I calculate the points where the nodes must be added, and then I add some supports, and I just run this script. And you'll see it executes quite quickly, and it creates that model. It's a solid model using the solid finite elements. I've got a cantilever beam there, and this type of thing will really take you a while to do with in the graphical user interface. Do it in code; it's a lot quicker. And even if you want to make changes to this, it's even quicker, because if you did this in the GUI and someone said no, you have to extend it or make it deeper or thicker, you'll have to start from the beginning, basically. Whereas with the script, you just change a parameter in the script, run it again, and it updates that for you. So really, prototyping is a lot quicker with this. Then the next example that I have here is one of my favorite. Because I made the script. It's one where I've got a hyperbolic a function, a hyperbolic cosine function, and I use that to calculate points and connect those with beams, and I've got almost like a catenary arch that I create with beams, and you'll see how that happens here. So import some materials, import some sections, and then I create a list for the x and y coordinates, and then simply I've got that function, the hyperbolic cosine function. In a for loop, I just run through it and calculate all of my coordinates, execute it, and there is the model. So this is like an arch. So it's if you flip that around, then you've got a very efficient arch, and I've now done it the other way around. So I'm just putting a support there and then a load there at the tip on the right, and you'll see this one. It's going to have quite a strange result that we get here, because it's not a very standard model. But again, you see that axial force, moment, and shear. It really is capable. And this is one place where if you've got something like this that you need to model, if you did this in the graphical user interface, you'd have a much harder time creating those nodes, whereas my script calculated it for me and it inserted it at those points. So you could do it in the graphical user interface, but you'd have to have a calculator or a spreadsheet or something next to you to calculate all of those coordinates, whereas the script just did that for me in one go. All right, so again, also not the most practical example, but here's the one that's going to be more practical for you. And this is one that I alluded to earlier. That's the one of a portal frame. So what I'm doing here is I've got a script that basically defines all of the members in the portal frame. So it's a column on the left, it's a rafter on the left, a column on the right, and a rafter on the right. And with a few lines of code, I can then create this portal frame, and it also includes boundary conditions and loads on this model. So you can see what it looks like. I've got some distributed loads on it there. So that's with a click of a button, it creates that for me. Now, this is where I think it helps a lot for prototyping, because if I were to see what happens with this model if I make the span 12.5 meters instead of 10, I just go and change the parameter in my script, run it again, and I've got a new model. And you could create 10 or 20 options like this, analyze them all, look at the deflection, look at the total mass of the structure, and really plot what's happening there and find the best configuration for your structure. So I think that's really where the pi sumo is worth its weight in gold. All right, so that's how you can do it. Now you might ask, or you might protest and say that you're not familiar with sumo or familiar with Python. How do you learn about this? Well, it's quite simple, and we've got some nice resources for you to learn from. And the first thing is the user guide, which ships with PySumo. So if you just click that little question mark icon there, that will call up the help file. And this help file, it introduces you to PySumo, shows you the scripting palette, and it even has some default code examples that you can look at. So there it explains to you how you address the material database, how you access the section database, and even some code snippets or samples that you can copy and paste and get going from. If you're interested in more, you can go to our GitHub page. There's a link, and you can copy whole scripts from our GitHub page and just copy and paste it into the scripting editor in Python. And once you have that, you could just execute that script, and it does whatever the script says it must. So here we go. We've created a wall. So this is a wall object. We can mesh it with finite elements later on. And that's just from a script. So if you are new to PySumo and you want to learn about this, then go to those resources. We have put in the chat a link to the Python website for more resources. And without knowing too much of Python, you can just combine a whole lot of our scripts. We've got scripts showing you how to load your model, how to add beams, how to add supports, all of these things. So if you can just combine those, you can build an entire model without knowing too much about the Python programming language. And by the way, it is quite an easy one to learn, so don't worry about that. Okay, so that's it for our PySumo interface. So please go and play around with that. It's definitely something that is going to grow also in the future. All right, then up next, we have our design link to the PileCap design module. Now, we are jumping the gun a bit here because we haven't talked about the PileCap design module. That's one of the new ones that Heino mentioned earlier. So you will learn about that later on. But what we're basically doing here is we've got a design link, so we could export our reaction forces to the PileCap design module and then design a PileCap based on those reaction forces. So here we go. We've got a PileCap supported by 4 piles and those columns. So all of our load cases have been brought in. Here are our strut and tie forces. So that's then used to calculate the reinforcing for this PileCap. We've even got a very nice calc sheet there showing you everything. So don't worry about that too much. I'll talk about this in more detail. This is a new module, so if you don't recognize it, it's not an issue. All right, so that's the PileCap design link. Then we've got our high resolution reporting, and again we had some requests from clients asking us that they want higher quality graphics on their reports because they export this to PDF and then clients zoom in on it and it starts pixelating. So we've increased this option, and you can, in your file settings in Sumo, you can toggle the amount of pixels that you want to export, so you can have really high quality graphics, and that's going to look great on design reports. Even if people display it on projectors and monitors, it will look good. Right, then we've got the Ultra HD display support. So believe it or not, we have clients that already have 8K monitors. I'm still stuck on a 4K, which I quite like, but 8K is really next level. And we've made sure that we support the 8K screens. So if you get one of those or are looking to get one of those, you can. We will be able to support you on that. Then the second to last topic that we want to cover in terms of Sumo is the prescribed displacements that we've added. So it's a small function that we've enabled in the supports properties palette. So you can see now for a point support, if you click on that support, then in your properties palette there's an option for a prescribed displacement. So what that means is we just before the analysis even conducted, we assume that we know what the displacement is at that point. We put that in the displacement vector, we fix that value, and then we can calculate what's happening there. So in this example, I'm assuming that the middle column is subsiding by 20 millimeters, and there we go. We've got actual force, X moment, and Y shear and that's the influence it has on the model. So in the absence of any other loads besides the self weight, we've got quite significant forces and stresses in the model, just because of that one column subsiding by 20 millimeters. So this is definitely something that you can use if you're looking at buildings or issues in construction, and you want to investigate what influence they have on the model. Right, and then the last major thing that we've added to Sumo is the IFC design transfer view, and this is, I think, really, it's in terms of modeling, it doesn't have a big influence, but really in terms of exchanging and connecting with other professionals, it's important. So what I'm doing here in this little demo is I'm just going to export this Sumo model. It's just a normal industrial warehouse frame. If you like, I'm exporting that in the IFC4 design transfer view, not the structural view. And then I can open this in something like Autodesk Revit. They've also expanded their IFC capabilities recently. So we could export this and then bring that into Autodesk Revit, and it brings in the entire model for us with its sections, center lines. So this is really a fully fledged model. It's not in place families or anything like that. So that's quite nice. You've got a complete model there. I know of clients also that have done this operation from Sumo to Tekla, to their product Tekla and Trimble, of course, and it also works well. So really something that you can use if you work with colleagues or other professionals that use different softwares. Okay, so that's it for the Sumo additions. So really quite a slew of new additions and things that you can go and look at. That brings us to the new modules that we've added, and we've got two of them. The first one is the column splice module, and that forms part of the steel design bundle. Then we've got the pile cap design module, and that of course forms part of the concrete design bundle. So we're first going to have a look at the column splice module, and the column splice module is just used to design bolted cover plate splice connections, and that's for I and H-shaped columns in your structure. So wherever you've got a column that's too long and you need to cut it in half for transport purposes, anything like that, you can use this module to design those splice connections. So typically we divide those splice connections into two categories. We've got bearing type and non-bearing type, and the ones we are looking at here today are of the bearing type, and that's the predominant ones used in the industry. So what that just means is the bearing type is where the actual force, so compressive actual force between the top column and the bottom column, is transferred by bearing. So it's the top section physically pressing against the bottom section that's transferring the compressive forces, and then obviously tensile forces are transferred by the cover plates. So that's really the load transfer mechanism. Non-bearing types, on the other hand, they have no bearing, so we assume that there's a small gap between the two sections, and both compressive and tensile actual forces must be transferred through the cover plates, and that's just the distinction that we have. But like I said, bearing types are the most common, and they also tend to be obviously the most economical ones. So typically you'll stay away from the non-bearing type. Right, so if we look at the non-bearing, or if we zoom in on the bearing type splices, then we can see that there are three types that are supported in this module. That's the external type, the internal type, and the division plate. So external and internal refers to the position of the cover plates, and you can see there on those little graphics that I've got there, the external cover plates are, just as the name suggests, they are placed on the outside of the flanges of the eye sections, and then also there's a small shim plate required to fill that gap. And the reason for that is because usually you might have different columns on top of each other. Then we've got the second one, we've got the internal cover plate. So that's just where the cover plates are placed on the inside of the flanges. And then the third type, which is quite a lot different from the first two, is the one where a division plate is used. And we use the third type when the two columns are not of the same serial size. You'll see now after this in my demo how that manifests, but when you've got two columns on top of each other that are of the same serial size, then you can use one of the two first ones, so either the external or the internal cover plates. But when the two columns differ quite a lot. So you've got a small column sitting on top of a large one, then the direct bearing is not possible without a division plate, and you require that to transfer the compressor forces. You'll see now in the demo how I do that. Then the type of loads that we can apply to these columns are usually of an axial nature, so either compressive or tensile. Tying loads that we consider in the buildings are obviously always tensile, so we assume that the columns on the lower floor may be knocked out, and then the building or the columns above that must be able to carry the entire load of the floor below it in tension, and that's where the tying loads come in. And then, of course, we've got our bending moments, which you typically have in columns. They aren't that large compared to the actual forces, but definitely most buildings have bending moments in their columns. Right, then let's just look quickly at the design checks that are performed by the module on bearing type splices. So there are 6 that we need to do, and these are typically recommended by your Eurocode design standards. And what we have here is the first check, which is really an important one, is the recommend detailing practice. So what that means is that your structure needs to, or your splice rather, needs to meet some minimum detailing requirements. So that means your bolts need to be of a certain size, your cover plates must be of a certain thickness, and your edge distances may also not be smaller than a certain distance. So a couple of limits that they set for you, but if you follow those guidelines, then you really have a very nice and sound connection that's easy to manufacture and should be safe. Now, we do those detailing practice checks for you, and even the automatic generation gives you a connection that adheres to those detailing practice guidelines. So that's something to note. Then we've got a couple of checks on the flange cover plates. You can imagine we need to check the tension in those cover plates, see if the plate resistance is enough, and then obviously the bolt groups, the bolts that are loaded in shear, they must be able to resist those shear loads. And then we've got a minimum resistance check there, so that's for the cover plates and the bolt groups. They must have a certain minimum resistance to be considered adequate. And then lastly is the tying loads. That's where I said in the presence of a tying load is where all other loads are neglected, and there's just a pure tensile load on the columns, and the connection, both the plates and the bolt group, must be able to resist that tying load. You can turn that on off if you want, but a lot of building codes require that you check the tying loads. Right, so that brings us to the demo, and we're going to do just a quick demo of this module, and you'll see that in this first example, I've got a column on top of another one, and they are of the same serial size. Yes, the one is heavier than the other one, but the serial sizes are the same. So that allows me to use an external or internal cover plate option. I've got some load cases there, load case 1 and load case 2, with temporary and permanent loads, ULS and serviceability. And then I'm going to design the column, of course, for that. There's even a tying load there of 100 kilonewtons. So remember, that's a tensile force on the column. And if we look at the design, we've got the button there that we can generate a splice connection. That generates a very nice connection for us, as you can see here with your bolts. So it looks like we've got 5 rows of bolts, 2 columns on each of the columns. So what's that? 20 bolts on each side that we need. Now, let's see if we can do the same one using internal plates. So because the serial sizes are the same, we can do that. Everything else remains the same, loads, and we are going to ask it to generate a connection for us. And you can see there's your connection. Notice that your cover plates are now internal on the inside faces of the column, and there's also no shim plates required anymore. But we now need 6 rows of bolts, so that shows you that the resistance is a bit lower. Now let's imagine for a second that the top column is not of the same serial size as the bottom column, so different sizes, and you can see there on your graphic those flanges do not line up, so bearing is impossible until we add a division plate, and that's really what we need to do with this connection. So if we generate a connection now, you'll see that we've got a division plate there, and those green plates are shim plates that we require to fill the void between the cover plates and the flanges. And then also we've got some small cleats there that just hold the cover plate and the column in place, making sure that it doesn't move unduly. And that's it for the column splice design. So really a nice one, and I can see this being used on on industrial steel projects. And typically, if you've got a tall building that's 20 meters tall and you spec one column for the, or in your analysis module, when you're building it in Sumo, it may be just one column, but for practical purposes, you won't be able to transport a 20-meter column, and then you might need to divide it into two. And that's really where you'll want to use this column splice to keep that column continuous, make sure that your connection is adequate, and then you're good to go. Okay, so if you find that interesting, I'm putting a link in the chat to this document, and this is the document that we use to verify our software, and it was published by the Steel Construction Institute and the British Constructional Steelwork Association, both respectable associations in England. And they give you some examples and guidelines for steel connections, and we use that to verify our module. So we are happy with our results. So I think you can rest assured that they are trustworthy and safe. So have a look at that document if this interests you. All right, then we've got our pile cap design module. That's also an exciting one, and I know something that people have asked for many times in the past. So what we're doing here is we're designing the pile cap, which is the interface between the piles in the soil and the column at the top. So this is almost a collaboration between the structural and the geotechnical engineer, because it's the interface between the top of the building and the soil. So it's really where the two disciplines come together, and that's what we do in this module. You'll see also the types of pile caps that we can design are pile caps that rest on 2, 3, 4, or 5 piles. And the reason why the number of piles are important is because in this module we make sure that the pile cap is a statically determinate problem, and whether there's 2 or 3 or 4 or 5 piles, it's always a statically determined problem. So that makes the analysis much easier and quicker, and we don't need to have a stiffness matrix or anything like that to solve that. So here is the module, and on the screen I've got a pile cap supported by 4 piles, and I would like to design the pile cap. So that's that square or rectangular part that you see in the middle there. Now, those of you that have done this before, you'll know that the pile caps are typically deep. So that means that we can't use your normal beam theory to design this, because it's not as simple as assuming that the bottom face is in tension and the top face is in compression. So we need a more rigorous analysis method for that, and that is why we've got the strut and tie analysis that we're doing here. So in red you can see the compressive strut, and in blue it displays the tensile ties for you. So all those forces are calculated. Again, it's a statically determined problem, and then from that we can then size our reinforcing for this pile cap. It is a reinforced concrete pile cap after all. So we need to first calculate those forces before we can then calculate our reinforcing. So here's your reinforcing. You've got your distribution steel, which you see there. You can toggle that, and then also we've got our tie reinforcing below that. So this is just the reinforcing that you're required to have an adequate pile cap, and you know that it's designed using the strut and tie method. So that gives you a very good solution as opposed to the beam theory, which is a bit it's a bit too conservative when the beams get quite deep. Right, so that's our pile cap design module. So very fun one, and I think one that will be used quite often. All right, that brings us to the continuous beam crack width that we've added here. So this was added on request from clients that we have in Southeast Asia, and they came back to us and told us that they want to see their crack widths in the continuous beam module. Now, most of you will know continuous beam. It's one of our most successful and most used modules, and you'll see that we've added the crack width there between the deflections and moments. And what that basically is it gives you, over the entire length of the beam, it displays the magnitude of the cracks. Now, these are flexural cracks, so in the tensile zones in the beam, you will see these types of cracks, and this is according to the Eurocode 2 guidelines. And of course, if we look at the cross section of the beam, or an elevation rather, we get those cracks in the sagging regions over there, and then also in the hogging regions, we've got cracks again. So this is something that we've added upon request from some of our clients. So something that we that you can use if you like to see that. And the idea here is that instead of checking your crack widths at the end of the design, when you've already put in all the effort, you can do that at design time, saving you time so that you don't have to redo the design if your crack widths are too large. And I think that's quite important when you're dealing with water retaining structures or any beam that's really by the coast where there's aggressive weather. Right, so this brings us to the last item in the PROKON 5.1 release, and that is the rework of the Eurocode National Annexes program. Now, those of you that make use of the Eurocodes, you'll probably know this module. It's been around for a few years, but we've improved it quite a lot. And one of the major additions that we've made here is that we've included the Singaporean National Annex to the Eurocode for Eurocode 1, 2, 3, and 4. So you don't have to add that manually anymore. You can just change your active country here, and it will then read those values from this module, and your local values will be used in your design. So you can see there we've got, by default, we're now shipping the Singapore and UK annexes in there. You could, if you're in another region in the world, you could add your own national annex. We don't ship it yet for you. We may ship more of them in the future, but in this case I'm adding Denmark, and what that happens is it just takes your default, it inherits the default Eurocode values, and then you can just go, if you have the national annex next to you, you can just add those values in, and if you make sure that that's the active country, then once you do a design according to Eurocode, then that value will be used. So rest assured about that. Okay, so that's it for everything that's new in PROKON 5.1. We hope you enjoyed that, and with that, I'm going to give over to my colleague Heino to wrap it up for us. Thanks, Heino.
Thank you very much, Johan. It's now time for a quick poll, and we appreciate your contribution. For the 3 questions for today are as follows. Which new Sumo feature do you find most useful? The second one, have you ever designed a reinforced pile cap? And the third one, would you like to see a column splice design link in Sumo? We'll just give it a few seconds for you guys to answer the poll. And we can now go to our Q&A session. And this is your chance to pose a question to our presenter. We already received a few interesting questions. And for our first question, how do I get PROKON 5.1?
All right, so you can get PROKON 5.1 by simply downloading the latest setup package from our website, or if you already have your software installed, you can just click live update and it will download the latest version for you.
Okay, and for our next one, when will the solid finite elements and Python scripting be included in Sumo?
It's already there. You just need to update to the latest version as we explained previously, either through the live update or downloading the latest version from the website, the setup, and then it will be included and you can make use of it.
And then our next question, I have a full structural bundle. Will I be able to use the two new design modules before my next renewal?
If you have the, if you subscribe to our full structural bundle, then yes, you do not have to add them separately. They are included in the steel and the concrete bundle, so you can just update and then you'll be able to use that. So it will be included for you.
Okay, and then for our last one, when applying loads on solid finite elements, can you only use floating loads, or are hosted loads also available?
Good question. So right now, the loading that we do to the solid finite elements are floating loads, because it's nodal loads that we're applying right now. So in the future, we'll definitely add some distributed loads, perhaps that you can load a face of the solids, and then that will have to distribute to the nodes in that area. But right now, it's nodal loads, so that means it's floating loads as it is. I know, interesting enough, there's another question by one of our attendees asking about the triangular distributed loads on the solids, and the answer to that is similar. Right now it's a floating load that you're adding, so what you'll have to do is you'll have to apply nodal loads and copy that. So you won't have that yet, but I'm sure it's going to come quite soon, that we include that. The solid finite elements are very new, so you can expect in the perhaps next year when we sit here, most of these things will have been added. So definitely something that you can look forward to. I see that there's a question asking about the recording. I think I'll answer that one too. This gentleman is asking, do we record this session? Yes, we did record the session, and we will publish it on our YouTube channel in a week or so. We just have to process it and cut out all of the waiting and the Q&A and things like that, which is not needed. But yes, we will publish that, and you can rewatch it later then on our YouTube channel. Right. So I see there's quite a lot of questions that we've got here. I think we still have a few minutes, so let's do a couple more. I know. So I see that there's another one that we have here, and this person asks, are these crack width calculations available when exporting beams through the beam detailing design link to Sumo? And the answer is yes. So for any beam design that you're doing, the crack width calculations are done. It doesn't matter if it's coming from the design link or you've got a standalone slab or beam. It is being done for any type of beam in that module. All right, then we've got another question here. There's one. Let me just go. There's a good one. Do I need to download Python separately? No, you don't have to. You could use your own Python installation, but if you install the latest version of Sumo, then it will download and install Python for you. So a lightweight version of that. So you do not have to. You don't have to install it separately. It will be done for you, and you can just start executing code if you're on the latest version. Okay. All right, let me check if there are any other interesting question. I'm just looking through them. Okay. Then, okay, there's an interesting one that I want to add here. There's one asking for crack width calculations in the pile cap module. So obviously the answer there is not yet, but what I can tell you is that we are looking at expanding the crack width calculations to other concrete design modules, things like the retaining wall, like the footing. So I assume it will be added, if that is done in the near future, it will be added to all of the concrete design modules. So perhaps you can look out for that and see, and that may work for you. All right, here's an interesting one asking about an offset for the pile cap design, and that's something that my demo was very quick. I didn't talk about that, but yes, you can have an eccentricity, so your column can be eccentric on the pile cap. It doesn't have to be in the center. You could move it to the sides or have any offset like that. So in that regard, it's very similar to our pad footing or concrete base design module, where you can also include a pad that, and it can even have biaxial bending loads on that column with an eccentricity. So very flexible in that regard. All right, then we've got a question here asking about can you design a pre-camber portal frame with the finite elements? So that's also an interesting question. Of course, you could model something like this with shell or solid finite elements, but I don't think that's worth the work. It's going to be a lot of work, and your model will be quite large. I would just say if you've got a portal frame that's perhaps pre-cambered, you could just if it was rolled, you could just have a circle there or an arc, and then vectorize that arc and have short straight segments of beams, and then you can just design it as you would anything else like that. But of course, yes, you can do it if you want to do the whole rigmarole of the solids and shells. It's going to be more work, but I think it's going to be a lot more accurate, perhaps. All right, let's see. Here we've got a lot of questions, so we're not going to get to all of the questions. I just want to mention that because our time is almost up. So I'll just select one or two more options, but those of you that do ask questions that don't get asked now, or that doesn't get answered today, we will answer that via email afterwards. If it's a support query, we'll just forward it to our support address, and then you can expect a reply via email on your support query, and we will assist you from there. So just give us an hour or two to wind down from the webinar. It does take a bit of practice to get this right. There's another question that I want to ask about the IFC. There's a person asking about IFC export to Revit from Frame. So Frame does not support the IFC file format, but there is a workaround. You can take your frame model, send it to Sumo, and then from Sumo to Revit through the IFC link. Otherwise, for you, perhaps it's worth it to look at the ProDesk link. Now, we've talked on webinars a lot about ProDesk. That allows you to have a bidirectional link with Revit from both Frame and Sumo. So perhaps if you want to go to Revit and you're a Frame user, I would suggest that you use the ProDesk link. I think that's going to be the best way for you to do that. All right. Okay. Okay, here's another one. I think we'll make that the last one. A person asking about the design codes that are available in the Splice module. Right now it's the Eurocode 3, and we are looking at adding more design codes to that. But for now, it's the it's Eurocode that's the predominant one in terms of the Splice. In terms of the Splice designs. Okay, Heino, I think that's it for the Q&A. This was very productive. Those of you that didn't get your questions answered, we will definitely answer your questions later on via email.
Thank you very much, Juan. Once again, that brings us to the end of this webinar. Please visit our website to stay updated on everything PROKON, and thank you for attending, and see you next time.